So what I want to do is look into some examples of ions or complexes, the oxidation state of the transition metal in these particular complexes, the coordination number, and the geometry. So if you're given a particular complex or an ion, you should be able to determine the oxidation state of the transition metal, the coordination number, and you need to be able to predict the geometry. These are some very, very common questions that you will see. So the first one we're going to look at is we have cobalt with 6 ammonias coordinated to it inside these brackets, and Cl3 on the outside of the brackets. Remember, when I refer to coordination number and we're looking at a complex, the only thing that I really care about is what's inside the brackets. What's outside the brackets, that counter ion, is going to allow us to determine what the oxidation state of the transition metal is. Okay? So in this particular case, we have Cl3 on the outside. Each chlorine has a -1 charge or a -1 oxidation state, and there's 3 of them. So that means outside of this sphere, we have -3 for the chlorides. That means inside this bracket, these have to be +3 because this produces a salt, making this thing neutral. In this particular case, then, we have to look at the charge of the ligand. In this case, we have ammonia, and the ammonia ligand is going to be neutral. So if you look at page, and I'll put a note up here, page 1031, there's a table with the common ligands. You're going to be responsible for them on an exam. One of those ligands on that table is ammonia. Ammonia is neutral, so that means that the cobalt must be a +3 oxidation state here. So the oxidation state of the transition metal is cobalt 3+. The coordination number is the number of the ligands that are coordinated to the cobalt, in this case, inside the brackets. So our coordination number is going to be 6, and our geometry is going to be an octahedron. So this is the thought process that you need to go through to determine each of these guys. Another example would be K3, and inside brackets we have NiCN5. In this particular case, the potassium is a +1 charge. There's 3 of them. So that means that the potassium is going to give an overall +3 charge to this complex. Inside the brackets, this NiCN5 has to have a total charge of -3. If we look at our ligand table, cyanide is a 1- charge, and there's 5 of them. So in order to give an overall charge for this complex ion of -3, that means the nickel must be +2. So the oxidation state of our transition metal would be nickel 2+. The coordination number in this particular case, we have NiCN5, so our coordination number is going to be 5. And the geometry can either take one of 2 geometries. It could be a trigonal bipyramid, or it could be a square pyramid. And in transition metal complexes, we cannot distinguish between these 2 geometries. So typically what we're going to observe is we're going to get a mixture of each of these. If I look, though, at something like K2 PtCl4, in this particular case, our potassium has a +2 charge, so that means the complex ion has to have a -2 charge. if there's 4 chlorides with a -1 charge, that means platinum has to be 2+. The coordination number here is 4. If we have a coordination number of 4, typically what we observe for these complexes is either a tetrahedral geometry or a square planar geometry. This particular case is square planar. If, on the other hand, I look at TiCl4, in this particular case, our titanium is 4+, the coordination number is 4, and the geometry this takes is a tetrahedron.